Hey everybody, welcome to the video where we are now going to revisit the hydrogen atom, but this time we have a better way to model the atom. Bohr's model worked okay. It did give energy levels for the hydrogen atom. It did explain the emission spectra for some of the different parts of the spectrum, but it does have shortcomings. It doesn't fully explain all the emission lines that you see, particularly when you place the hydrogen atom in a magnetic field. You find out that you see more emission lines, more energy levels seem to come out of nowhere when you do that. Also, we know that the model of the electron going around in a circle, that's just not right. With the advent of quantum mechanics, we have a more sophisticated way to model the hydrogen atom. So we're going to see what happens when we take the time-independent Schrodinger equation, which is sort of the formalization, if you will, of quantum mechanics. See if we can find that eigenfunction for different states of the hydrogen atom. And we'll find out that it is successful. But even this model, as you'll see, has to be fine-tuned a little bit, and I'll mention that when we get to that point. But let's start off then, I'm calling this section atomic physics because we're back to trying to model the atom, but this time again with a more fully developed theory of quantum mechanics. So what we're going to do again is we're going to look at the hydrogen atom, because that's the simplest atom. So regular old hydrogen, we have the proton. The nucleus there is just one proton, and we have this one electron, right? Okay, and in the simple planetary orbit model, it's just orbiting around, yes? Well, that's supposed to be centered. I'm so sorry. In fact, I'm not happy with that. It just doesn't look good. So where's my eraser? Sorry. Okay. Now I'll draw my nucleus more in the center. There we go. That looks better. Okay. All right. So what we do is, if you recall the one-dimensional time-independent Schrodinger equation, it looks like this: minus h bar squared over 2m d squared psi of x, little psi of x, dx squared, plus potential energy function, which would be a function of position, x, times psi of x equals the constant energy, the energy of one of these states, times psi of x. So that's what it looks like in one dimension, right? Now, the problem is we can't really model this in one dimension. We're going to have to go to 3 dimensions. Okay, so if you recall, we know how to describe the potential energy interaction of 2 charged particles. So the electron, just like in the Bohr model, via the electric force, the attraction to the positively charged proton, is going to pick up a potential energy function. But we know that that potential energy function in 3 dimensions, it's going to be a function of that distance r, and it's going to be minus k times the fundamental charge squared over r. So we could go and just make this a 3-dimensional equation, right? And this is where some Calc 3 stuff comes in, some vector calculus. So in 3 dimensions, what you would do is, instead of having just a second derivative with respect to one variable, x, you would have this del squared. So you would have what we would call the Laplacian. You guys probably discussed this in Calc 3. So that del squared, and now psi is a function of x, y, z, right? And then we would have plus, we would have this u, right, which we could write as a function of x, y, z times psi of x, y, z equals a constant e times psi, which is a function of x, y, z. Okay, and if we're using rectangular coordinates x, y, z, this Laplacian that you see right here, right, that's just shorthand for d squared psi dx squared plus d squared y dz, dy squared plus d squared psi dz squared. So it's just the sum of the second partial derivatives of psi, okay? So that's not too bad, the form of this Laplacian in rectangular coordinates. Unfortunately, though, if we go to write u as a function of x, y, z, what we would have to do is we would have to write it like this. And it is just a function of this distance r, but if we're using rectangular coordinates, that r is going to be the square root of x squared plus y squared plus z squared. Ooh, now that is really messy. If we're trying to solve this differential equation down here, and this u function is the square root of x squared plus y squared plus z squared in the denominator there, that is a mess. It's messy, messy, messy. So what we do instead is, instead of using rectangular coordinates, we say let's use spherical polar coordinates. And again, this is a nice application of what you guys talked about in Calc 3. So spherical polar coordinates. And I'll remind you guys that in spherical polar coordinates, what you do is, let's see if I'll sketch this. Okay, so this would be the x-axis. That's the way I'll do it. Oops, I'm sorry, that's the y-axis. Coming out of the page would be the x-axis. So the xy plane is coming out of the screen, and then this would be the z-axis. This is one way you could set your axes. And if you have some point here, right, and I'm going to project it down into the xy plane, like that. So if you project it down, there is a shadow of it, a projection of it in the xy plane. Well, what you do to locate this is you give the distance from the origin, that's your r. Then you give the angle in the xy plane, like that, right? And physicists, we call that angle phi. Mathematicians call that angle theta. And then you give the so-called azimuthal angle, which is the angle from the z-axis to that line r. And in physics, we call that angle theta. Mathematicians call that angle phi. I know, it's confusing. Okay, so your coordinates are theta and phi. Okay, r theta and phi. Instead of x, y, z. Now, the nice thing about that is your potential energy function is now just a function of this r, right? You can write, as you see up here, u of r is just minus ke squared over r. So that's a nice simplification. The problem, though, is if you look at the Laplacian in spherical polar coordinates, it's not quite as nice, right, as you see here. And in rectangular xyz coordinates, the Laplacian is just d squared right psi dx squared plus d squared psi dy squared plus d squared psi dz squared. Do you recall what it is in spherical polar coordinates? I'm not going to write it down. I'm just going to go to Wolfram and I'll show you guys. It's right here. Can you see equation 1 right there? I might make it a little bit bigger. Ooh, that looks really nasty. Well, it turns out it's not as nasty as you think. You can actually solve the differential equation. We're not going to do that, but I'll just outline it. But if you use that version of the Laplacian, you can actually solve this differential equation. And again, what you do is, you've done this in differential equations, you assume that your eigenfunction, your r theta phi, right, is separable. So you can write it as the product of some function, I'll just call it capital R, which is only a function of little r, some capital theta function, which is only a function of theta, times some function I'll call capital phi, which is only a function of phi. So you assume this, and you put that in there, you take the Laplacian, and then you apply boundary conditions. Just like we did for the one-dimensional infinite square well, you apply boundary conditions. So what are the boundary conditions that you apply? Well, you actually apply boundary conditions on each of these three functions that I have written here, the big R, the big theta, the big phi. So what's the boundary condition on big R? Well, that has to go to 0 as R goes to infinity. We know that this function, right, because the square of this function represents a probability, right? We're not worrying about the temporal dependence, the dependence on time, but so the square of this is still going to represent a probability. It's not just going to be at a certain time. It'll be for that state, right? You can talk about where is the most likely place to find the electron, and that's going to be given by the square of this little psi. So you have to be able to find the electron for some value of little r. So that makes this function big R go to 0 as little r goes to infinity. It has to vanish. If not, the probability, right, wouldn't be 100%. It'd be greater than 100% of finding the electron, which is not physical. So that's one boundary condition. That condition leads to, so the boundary condition on R is going to lead to a quantum number. Then there is the boundary condition on theta, is that if I go, right, if I go once around, so you can imagine that theta, right, I have some value of psi. If I add 2 pi to that, I have to get the same value again, because of going just once around the circle. That leads to another quantum number. And then there's a similar condition on phi, that if this angle little phi, if you add 2 pi to that, you've got to get the same value for capital Phi. That leads to yet another quantum number. So the application of these boundary conditions lead to 3 quantum numbers. Okay, and that's what we're going to talk about now. So what are the 3 quantum numbers that it leads to? Okay, that is summarized in our summary notes. Okay, so let me go to the summary notes and I'll show you guys. I made this table for you. So the 3 quantum numbers that come out of these boundary conditions are the following. You have little n, which is called the principal quantum number. Now, what does it quantize? And you should know what these what these quantum numbers quantize. It quantizes the energy of a particular state. And how does it do that? Well, the form should look very familiar. It's E equals minus what I'm calling Z effective over n squared times 13.6 eV. Now, if this is just the hydrogen atom, Z effective is 1. Okay? Turns out we can actually apply our results to other atoms. And then Z effective is going to depend on this principal quantum number n and also on the next quantum number. Okay, so it's a more complicated dependence. If we just think of the hydrogen atom, that Z effective is just 1. So you see that we actually do get, for hydrogen, the results of Bohr. We get minus 13.6 eV over n squared, just like he did. Okay. All right. So what are the allowed values of this principal quantum number? Just like Bohr said, 1, 2, 3. Okay. All right. What's the next quantum number? That is symbolized by lowercase l, and this is known as the orbital quantum number. Now, what does it quantize? It quantizes orbital angular momentum, which we symbolize by big L. If you remember, Bohr's fourth postulate was that the orbital angular momentum of the electron could only be certain values. He said it was n times h bar. Well, turns out it's a little bit more complicated than that. He's right that the orbital angular momentum is quantized, but it's a little bit more complicated. In fact, here's the dependence. The size of L has to be the square root of this orbital quantum number L times that number plus 1. Then you multiply that radical, whatever that number is, times h bar. Okay, so let me go back to the notebook and I'll jot that down. Bohr's result was that L was n times h bar. Okay, n times h over 2 pi. This is Bohr's result, and this is not quite correct. The actual, I'll call this quantum mechanics result, is that the size of this is, I'm going to use a script L, little l times little l plus 1. That's underneath the radical sign, and then you multiply by h bar. Okay, now, again, the way you can picture this is, let's suppose I'm going to try to do a three-dimensional rendering. See, here's the electron orbiting, and let's say it's going this way, okay? What you can do is, to figure out which way the angular momentum is due to that orbiting electron, if you take your right hand, make your thumb perpendicular to your fingers, trace the electron as it goes around the nucleus with your fingers, your 4 fingers, your thumb will tell you which way that L vector points. So my L vector would point like this. Okay, that would be the vector direction. And what quantum mechanics says is that the size of this L vector, the magnitude of it, is fixed, okay, according to this equation. Now, what are the allowed values of L, right, for a given state? Okay, again, a little bit more complicated, because in the Bohr model, we only have one quantum number, and so far we have 3 right here. Well, the allowed values of this little l are going to be 0, 1, up to n minus 1. So the principal quantum number is going to determine what the allowed values of the orbital quantum number are. So for instance, if you're in a particular state, the electron's in a particular state where n equals 1, well look, n minus 1 is 0, so the only possible value for this L is going to be 0. However, if you're in a state, the electron's in a state where n equals 2, what's n minus 1? That's the maximum value for L. Well, that would be 2 minus 1, 1. Oh, so in that case, L could be 0 or 1, because it starts at 0 and goes to n minus 1. And similarly, if n equals 3, well then L, little l, could be 0, 1, or 2. Okay? All right, and you'll see in the summary notes that the allowed values I wrote as 0, right, 1, comma, up to n minus 1. So you have to check what n minus 1 is first. Okay, now what's the third quantum number? Okay, that's usually symbolized by m sub L, that's m subscript L, and this is commonly called the orbital magnetic quantum number. What does it quantize? It quantizes the z component of orbital angular momentum, L sub z. Okay, and how does it quantize it? Well, L sub z is the orbital magnetic quantum number, m sub L times h bar. And what are the allowed values? Well, the allowed values of m sub L are going to depend on what is the value of little l. Because m sub L will go from minus little l in integer steps to plus little l. Okay, now you're like, what? I know, that's a lot. First of all, let's talk about this z component, right? So in my picture right here, you could imagine that I have a z-axis like this. You guys see it? That's my z-axis. So this L vector has a certain z component, L sub z. And the quantization condition is that this L sub z can only be m sub L times h bar. Now, the first question is, well, what determines the z-axis? Seems sort of arbitrary to me, right? I mean, we always take it to be up, but what is up, right? You know, if I have these hydrogen atoms flying around, what determines the z-axis? Yeah, it's a good question. Okay, the answer's sort of weird. You have to have some experimental condition that determines the z-axis. And what I mean by that is, you actually only see evidence of this quantization when, for instance, you put the atom in a magnetic field. If you put the atoms in a magnetic field, the direction of that applied magnetic field actually determines the z-axis, because there's an interaction of that applied magnetic field with the hydrogen atom, with the electron. That interaction actually causes some energy levels to split, to develop into two or more energy levels. That interaction is explained by quantum mechanics as a quantization condition on the component of the orbital angular momentum that is parallel to the applied field direction. So again, it's the experiment itself that's determining this z-axis, because it's the interaction of this magnetic field that's causing the interaction with this quantization condition, this L sub z. Okay, so it is strange that the experiment itself is determining the z-axis. Okay, so what are the allowed values of m sub L? Well, again, m sub L can go from minus L in integer steps, 0, up to plus L. So if you look up here, let's look at this one. If n equals 1, the only value of little l is 0, well then the only possible value for m sub L is going to be 0. Because if I start at minus L, I'm starting at 0. I can't go anywhere but 0. Over here, when n equals 2, we said L could be 0 or L could be 1. Well, if L is 0, we could have an m sub L of 0. That's it. But if L is 1, we could have an m sub L of minus 1 plus an integer, 0 plus integer plus 1. So we actually could have a state that has n equal 2, L equal 1, m sub L equal minus 1. Or we could have a state n equal 2, L equal 1, m sub L equal 0. Or we could have a state n equal 2, L equal 1, m sub L equal plus 1. Okay, so, wow, there are a lot more states now that are predicted by quantum mechanics than Bohr's model. Okay, yes, that is true. Okay, all right, so those are the three quantum numbers, right? But there's more than that. Now, this doesn't come from application of the Schrodinger equation, but this came from another historically important experiment called the Stern-Gerlach experiment. People were able to actually bend when they would send hydrogen atoms, right, in magnetic fields. They would actually be able to bend them one of two ways. They would see one of two directions. And they were puzzling. Like, why are we only getting two directions? What's going on here, right? Well, it turned out it was an interaction of the magnetic field with what's called the spin of the electron. Okay, so, and again, this doesn't come from application of the Schrodinger equation. It comes from other experiments. But the way we model this is, in addition to the electron orbiting the proton, the electron is spinning. It's like a little ball of charge in this picture, spinning on its axis. Very similar to how the Earth rotates on its axis as it's orbiting the sun. So there is a spin angular momentum associated with the spinning electron. So this vector might be pointing like that, right? And again, you can imagine taking your right hand, rotating your fingers in the direction of the spin, follow the spin of the little ball of charge. Your thumb will give you the direction of that spin angular momentum. And we usually symbolize that with a capital S. I'm going to put little bars on this, on there to indicate that's a capital S. Well, it turns out that that magnitude is quantized. Okay, so that quantization you'll see right here. Okay, there is a quantum number called little s, the spin quantum number, and what it quantizes is the size of that big S vector, the spin angular momentum vector. How does that quantization look? Oh, in fact, it's identical to how the orbital angular momentum is quantized by the orbital quantum number little l. The spin magnitude is quantized by the square root of this spin quantum number, little s, times little s plus 1. Oh, that's all underneath the radical. Then you multiply by h bar. Now, it turns out for the electron, there is only one possible value for that little s spin quantum number. It's 1/2. Okay, so the size of this vector then, the size of this vector is fixed for an electron. In fact, the size of the spin, the magnitude of it, is going to be the square root of little s, which can only be 1/2, times little s, which can only be 1/2 plus 1, times h bar. So 1/2 plus 1, that's 3/2, times 1/2, that's 3/4. So the size of this spin vector is always going to be radical 3 over 2 h bar for the electron. Okay? All right. Well, just like in an experiment, when you determine the z-axis, you find out that the z component of orbital angular momentum L is quantized. The same thing happens for the spin angular momentum. The z component of it is going to be quantized. And what does that quantization look like? Oh, it's just like the quantization of the z component of L by the orbital magnetic quantum number m sub L. So we introduce a spin magnetic quantum number, m sub s, and we say it quantizes the z component of spin angular momentum, s sub z, and that quantization looks like the m sub s times h bar. And the allowed values of m sub s depend on s, just like the allowed values of m sub l depend on l. So you start at minus s, and you go in integer steps to plus s. But remember that this little s can only be 1/2. So that means m sub s can only have two possible values, minus 1/2, and then add integer 1, or plus 1/2. So there are only two possible values for m sub s, minus 1/2 or plus 1/2. Okay? All right, so if we take the results of the Schrodinger equation applied to the hydrogen atom, right, and we add this spin stuff that was experimentally found, okay, we actually have 5 quantum numbers that describe a state of the atom. Those 5 quantum numbers are n, l, m sub l, little s, and m sub s. But because this little s, the spin quantum number, can only have the value of 1/2, people tend to forget about it. And they say, well, really, you just need 4 numbers to define an allowed state. N, L, M sub L, and M sub S. There really are 5, but because S never changes, people don't worry about it. Okay? Now, those 4 then quantum numbers, forgetting about this S equals 1/2, those will determine an allowed state. Okay? All right. Now, the way you can do this is, as you see here. So you can refer to a state with N, L, M sub L, and M sub S. Okay? All right. In the next video, we're going to continue with this, and we'll look at, what sort of range of quantum numbers can you have, right? And we'll talk about implications of the fact that these quantum numbers are defining a state. Okay. Okay. I'll see you in the next video.